Hello and welcome to part 1 of 2 on earthquakes and faults. In this 2-part lecture, we're going to go over what faults are and how breaking of faults in the form of earthquakes creates seismic waves and hazards. You can find supplementary information on this in Marshak, The Essentials of Geology, Chapter 8. Okay, so before we get started, I would like to think through this question of what controls earthquake risk. This is a question you're going to be working on throughout this lecture, so I would write this down and record your thoughts now. But essentially, I would like you to think of a few places, 3 to 5 places that you have been. This could be your hometown where you live. It could be someplace you go on vacation. It could be your college town, so Colorado Springs. Or it could be someplace you go where you visit family or something else, just some place that means something to you. And of these 3 to 5 places, I'd like you to compare the earthquake hazards within them. Which one has a higher earthquake risk? And here we're going to combine hazard and the occurrence of hazards as the earthquake risk. All right, so write that down. And once you've written that down, let's go to the next slide. Okay, so before we really get into earthquake risk, I would like to think about plate boundaries and how those are related to earthquakes. So if you remember, we went over three plate boundary types earlier in these lectures. We had our divergent boundaries, our transform boundaries, and our convergent boundaries. So in divergence, we have plates moving away from each other, like we see in this top image here. Transform has plates moving side to side, and convergent has plates meeting together with one subducting under the other. And yesterday we talked about types of volcanism at these. So we recognize that stratovolcanoes are normally associated with convergent boundaries, and we tend to get some shield volcanoes or fissures in divergent boundaries, and didn't really expect to see anything in transform boundaries. And today we'll flip this to think more about what earthquake types we expect to see at each of these boundaries. Right, so we'll start off with divergent boundaries. This is where we have 2 parts of the earth moving away from each other. And in divergent boundaries, it is 2 tectonic plates. However, when we think about faults, we can think of things on much smaller scales. So this doesn't have to be 2 tectonic plates. It could just be 2 parts of the earth within a plate moving away from each other. And if you can see my video, I'm going to do a lot with my hands. So I really like to use my hands to simulate earthquakes in regards to motion. All right, so we've started out here, we've got a purple plate and a green plate. And in divergent boundaries, which are going to result in normal faulting, the 2 plates are going to move, the 2 sides are going to move away from each other. In this case, the purple one ends up moving down and the green ends up moving relatively up, right? And so this is what's going to have to happen in order to accommodate more space. Now let's give these some names so I don't have to keep using their colors. We're going to call the purple one the hanging wall and the green one the footwall. These are not arbitrary names. Instead, it has to do with their relation to the fault. So the fault is this line that separates them, or the plane really that separates these 2. And if you were standing on this fault, like you were mining along the fault, maybe you're mining some precious minerals that are found along fault lines, your feet would be standing on the footwall, and you would hang your lantern on the hanging wall. So this is actually the origin of these names. Faults are really great places for fluids to travel along and leave behind precious minerals. And so from mining terminology, we have that the footwall is where your feet are, and your hanging wall is where you would hang your lantern, right? So it's kind of what's above you, right? And so we can define normal faults, not necessarily that they're extending, but we can say more specifically that the hanging wall is moving down relative to the footwall, and the footwall is moving up relative to the hanging wall. right? So that is critical to remember, and we're going to start to call this now normal faulting. So we will recognize that normal faulting is related to divergent boundaries, but it doesn't have to occur at divergent boundaries. And we'll talk a little bit more about that. Okay, when we look at convergent boundaries, we're now thinking about the exact opposite thing. We have two areas coming together. So if you put your hands together at an angle, pretend they are the two sides of this fault. How do they have to move in order to squish things together? So you want less space overall. Does the purple, the hanging wall, does it have to go up or does it go down? Hopefully you answered that the purple wall, the hanging wall goes up while the foot wall goes down. This is what occurs in convergent boundaries, which is also what we call reverse faulting. And in reverse faulting, we're going to have a hanging wall going up relative to the foot wall, and the two sides are really coming together. So if you're ever uncertain, just try and do this with your hands. If you push your hands together, you're going to have that action of, the hanging wall going up relative to the foot wall, versus if you have your hands together and you pull them away, that hanging wall is going to go down relative to the foot wall. Okay, and last but not least are strike slip faults. So this is going to be along things like transform boundaries, where we don't have any tension and we don't have any compression. Instead, we have side-to-side motion. And because it's side-to-side motion, we can't really describe either of these as the hanging wall or the foot wall because the fault itself is vertical. So we have instead two subtypes of this where we'll talk about what are the motions relative to each other. So we can use the unicorn as our stationary point. And if we're the unicorn and we're looking across at the purple block, whichever way the purple block moves relative to us is going to be what defines what we call this fault. And we'll just note this fault is called strike slip faulting. And in this case, the purple block moves to the right from the viewpoint of the unicorn, and so we call this a right lateral strike slip fault because it's moving to the side laterally in the right direction, right? The terminology is the same, whichever side you're on. So if you were to switch viewpoints to be from the trees instead of from the unicorn, so standing on the purple block instead of the green block, you would still see the other block moving to the right. So it doesn't matter which side you're viewing from, this is going to be a right lateral strike slip fault. And you can imagine the opposite would be true as well. In terms of terminology, we often draw an arrow for this. So in a right lateral fault, that purple block came closer to us. And so we're looking at here, pretend there's a three-dimensional arrow and it has fletching and it has an arrowhead. This symbol with the circle with the dot in the middle of it is looking down that arrowhead because this block is coming towards us. We're looking at the front of the arrow versus the green block, which is moving away from us. We're looking at the fletching. So that's what those two, that kind of X form in the circle is supposed to represent. We can have the opposite occur where instead of the trees moving to the right, they can move to the left like this. And this would just be called a left lateral fault. And we would have the opposite notation here in terms of those arrows where now the green block is coming towards us. And so we have the arrowhead. And then the purple block is moving away from us. So we have the fletching of the arrow. Okay, so let's look at some faults and see if we can figure out what they are. So here is a landscape. We're looking at a view from the sky, so somewhat oblique aerial view here. What kind of fault do you think this is, and where is the fault? All right, so if you're ready to reveal the answer, you can unpause and start here. So the fault is going to run about here where I drew this red line. And I can tell this because when I'm tracing each of these colors, so if I just look at this tan color here, the fault is where that color ends, right? And it's true for all the other layers. If I trace them along, at the fault is where they end. And I can actually meet up some of these layers too. It looks like we've got a tan layer that tends to form large hills here, and there's a tan layer that forms large hills here. That tan layer to the right has a slightly more yellow layer. We see that over here as well. Then it has some white layers, and eventually those white layers transition to being red. And we see that on both sides. This tells us also what the motion of the fault is. So we're seeing some lateral offset. Things are moving side to side, right? And which way are they moving? Well, if we were on this side and we're standing at the boundary between the white and the red layers, we would have to look to our right to find that same boundary on the other side of the fault. So this is a right lateral fault, a right lateral strike slip fault to be complete. Okay, we'll do another one of these. This time we're zooming in a little bit with scale. So now we're definitely not looking at something that could be plate tectonic in scale, but it's probably some faulting that's occurring within one plate. So even though the plates seem like they're rigid bodies, there is still some deformation going on within each plate. Okay, so same question. Where is the fault and what kind of fault is this? And now we're looking from the side. All right, if you're ready to share. So I'm going to draw where I think the fault is. There's a fault here, and there's another fault there. And just like the last time, I identified where the fault was based on tracing a single layer and seeing where the layer ended, right? So this top red layer was a great place to start. It ends here and then picks back up over here. And so there must be a fault between those. That also allows me to see what the relative movement was. But before we do that, let's identify what the hanging wall and what the foot wall is. So take a second, and when you're ready, unpause. So if we were a person standing along the fault right here, we would hang our lantern on this side, we'd be standing on this side. So this is our hanging wall, and this is our foot wall. Okay, now that we've identified which is the hanging wall and which is the foot wall, let's take a look at this red layer again, here and here. Did the hanging wall move up or down relative to the foot wall? It looks like the hanging wall moved down. And so if the hanging wall moves down, what type of fault is that? And if you need help, remember to use your hands. So the hanging wall is going to be that hand that's on top. In order for that to move down, you need to be under tension. You need to be creating space. And so that is going to be a normal fault. All right, there was another fault on this side here, then re-outlining again. And this is, if we go through those same steps, we're going to see that this is also a normal fault. Okay, and now we're zooming in even further in scale. So here we have a rock hammer for scale. A rock hammer is the size of a normal hammer. It just has one pointy end and one blunt end. So from this, can we answer the same question? Where is the fault and what kind of fault is it? And here we'll just note the view is from this side. All right, so take a few seconds to think about this. Pause your video, and when you are ready to proceed, unpause the video. Okay, so I traced the layers in order to figure out where the fault was, basically where those layers were broken up. And this one's a little bit difficult because there are a lot of faults, right? So I traced one, the main one right there. However, there's a lot of other areas where there are some offset. Right? And some of these are a little bit harder to trace all the way through. So we're just going to focus on this first one that I drew. I'm going to consider this to be the main fault. Okay, so let's do the same thing we did last time, identifying the foot wall and the hanging wall. So this lower one is going to be the foot wall, and the upper one is the hanging wall. Now let's think, which way did they move relative to each other? So I traced this tan layer here. What I see is that tan layer has moved up relative to its position along the foot wall. And so when I do that with my hands, in order for one of my hands to move up, I need to be compressing them together. And so this is going to be a reverse fault. All right, so those are great practices. And I think one thing that it showed us is that we can see those faults away from plate boundaries. A plate boundary is not going to be as small as this example here with the rock hammer. This here is some deformation and some faulting that is occurring within one plate. Another way to look at this is a map of all of the faults in Colorado. Colorado sits squarely in the middle of the North American plate, so we're nowhere near any of these plate boundaries, but yet we have plenty of faults here. And this is due to intraplate movement. So within the plate, there is still some motion to accommodate tension and to accommodate stresses. So two faults for us to think about, in particular in Colorado Springs, are the Ute Pass and the Rampart Range faults. So if you're in Colorado Springs and you can look out and look west towards Tapa, towards Pikes Peak, which is behind me in my virtual background, you may note that we have a fairly flat landscape that very suddenly rises to the Front Range. And that sudden break in the topography is where the Ute Pass and the Rampart Range faults are. These are faults that originally, about 65 million years ago, were reverse faults when we were first building up the Rocky Mountains, but recently have been reactivated as a normal fault. So this is kind of an interesting thing to think about. Once you have a fault plane, you have this plane of weakness. And so when the regional stresses change, you can actually change what that fault type is. If you go from 65 million years ago in reverse fault, we had tensional stresses that more recently have transferred to extensional stresses. Right, so in addition to getting earthquakes within plates, we can also have earthquakes occurring at different depths within the tectonic plates and not necessarily just at tectonic plate boundaries. So this is going to be an important classification, especially when we think about hazards, because the depth at which earthquakes occur and the energy is released at is really going to affect the amount of shaking that we feel on the surface. So I think this is a really nice example from Cascadia. Cascadia is the boundary between the Juan de Fuca plate in the Pacific Ocean with the North American plate. From 0 to 70 kilometers depth, we have what are called crustal earthquakes. These are shown in yellow in this diagram. And these are all earthquakes that are occurring along faults that are within the crust. So these are not interacting with the major plate boundary. These are also fairly shallow, so can present some additional dangers in that sense. A bit deeper than that, from 70 to 300 kilometers, we have deep earthquakes, and that's shown in purple. These purple earthquakes and these deep earthquakes tend to occur near the plate boundaries, in this case near the convergent boundary. And then we can get even deeper earthquakes at 300 kilometers depth or more that might be on the plate boundary interface itself. So kind of at the very limit of where we'd actually see any earthquakes. If we get too much deeper than this, deformation occurs in more kind of ductile ways. And so rather than these sudden breaks and brittle deformation, we might have a smoother process that's taking up some of the stress. When we talk about earthquakes, we're going to have two main names for the earthquake. The first one is the hypocenter, and this is where the earthquake actually occurs. You may also see this as the focus. And this is the actual location of the earthquake with depth in the earth. So it's the star in this diagram. However, when we're talking about earthquakes in a social sense and talk about the hazards associated with them, it's useful to talk about where they actually occur in relation to cities. And so that's where the epicenter comes in. This is directly above the hypocenter where the earthquake intersects with the surface of the earth. So this is what you're going to see reported in the news when you see that an earthquake occurred 70 kilometers away from a place. It's talking about 70 kilometers away on the surface of the earth is the epicenter. And there's going to be two main components to this. We're going to go over motion right now, and the second half we're going to go over seismic waves. So when the earth breaks along a fault, there's going to be motion along the fault that occurs, and that's the physical action of rocks breaking. And so we'll talk a little bit about what happens physically when an earthquake occurs in terms of the rocks fracturing. The second half, that's going to be what we care about in terms of hazards, is the seismic waves. This is the energy that's released from that earthquake and from that motion, and that's going to travel along up to the epicenter and up to many other places along the Earth's surface. Okay, so the actual movement of the fault and rock breakage is something we didn't really start to understand until the early 1900s. After the San Francisco earthquake in 1906, Reed developed the elastic rebound theory. And this is essentially the idea that rocks are acting kind of like a rubber band. Like between earthquakes, you have this tension building up, this elastic deformation. So that's essentially you're stretching the rubber band. Nothing permanent is happening. There's no energy release. But eventually you reach the limit of how far you can stretch that rubber band, and it's going to break or snap. And that breaking or snapping releases a lot of energy in the rubber band. You can feel it as heat on that rubber band. And with earthquakes, we can feel that as the rock breaking and an earthquake occurring. This is a nice illustration of that to take it away from necessarily just the rubber band view, where we have, perhaps originally the surface may look like this. However, there are tensions acting on the earth, and that starts to slowly deform it. So this is what's called deformation. And this is not permanent deformation, right? This is sort of that bending of the elastic. Eventually, however, the deformation reaches a breaking point where you cannot just slowly deform the earth like this anymore. It cannot just bend, it needs to break. And so that's where we get the rupture and the release of energy. And after that rupture, the rocks are going to rebound to a new shape. Unlike a plastic band that rebounds to its exact same shape, the earth doesn't undergo completely plastic deformation. And so there is some permanent deformation that results after an earthquake. All right, so this can be thought of also as an earthquake cycle. We start out with an original position that is deformed, that is then ruptured, and that leaves us with some offset in the earth. And then the cycle kind of builds back up again. If you want to think about this graphically, we can look at the comparison of stress versus strain over an earthquake cycle. So stress is the force that's applied, and plate tectonics is going to be that driving force for the stresses. Even for earthquakes that occur within a plate itself, that is often driven by some plate tectonic stresses occurring far afield. Stress may result in strain. So strain is the physical deformation that results from stress. Stress is the force, strain is what you see. So when we first look at an earthquake, we're going to get some elastic deformation. So stress is going to build up on the ground, and we're going to get some strain, but that strain is elastic, which means that, like that rubber band, it is completely recoverable. There's no permanent deformation. However, we often reach a ductile limit, or the elastic limit, which then transforms us into ductile deformation. And in this case, increasing stress is resulting in some strain. And it's still that kind of smooth strain. So we're still that fence post that is slowly moving like this. We haven't broken it yet. But the ductile deformation is not going to be recoverable. some of it is going to be permanent strain. At the end of ductile deformation, we reach brittle failure. And this is where the amount of stress has surpassed what the rocks can actually take up. And so there's going to be cracking, failure of that plane, resulting in an earthquake. And the amount of strain is going to progress along this dashed line back to this bottom level. And the difference between where we started and where we end is the permanent strain, or the offset that's caused by an earthquake. And you'll note that that amount is proportional to that amount of strain that was traveled during ductile deformation. Okay, so that is the end of part one. In part two, we're going to take where we just left off with brittle failure and an earthquake and translate that into seismic waves and think about how those travel through the earth and the hazards that they cause. But I would like you now, before you start with part two, to go back to your original hypothesis, where you came up with 3 to 5 places. I'd like you to now think about where those places are relative to plate boundaries and to faults. And no need to necessarily look this up. We're going to come back to this idea at the end of part two. But this is where we can start to categorize what is the hazard at each of these places.